If you see our last day discussion, so what we have observed or what we have done is the simplest thing, like to try to understand the behavior of velocity versus electric field curve. So you can see that your velocity in this direction, right, which is a factor of 10 to the power 7 centimeter per second, and with electric field, okay, kilovolt per centimeter. You can see it's very clear, right? The thing is that if it is a silicon, so the slope of this curve, if you see the slope of this curve, this is the slope of this curve, the slope of this curve up to this level. If you try to draw the slope, right? The slope of this curve up to this level, so you can calculate V is equal to mu E, right?
Sir,
Yes.
are you recording this lecture?
I think it's recording. I just now initiated it. It is recording.
Yes, sir.
Okay. So if you see the velocity of the car, so you can easily understand that it's a velocity is equal to mobility into electric field, right? So this part. But you see this curve is kind of linear curve, I mean like linear relationship. So this is value up to some linear linear behavior, right? This is not validating like when it actually bends. So you can think about this curve also. Control J. So this curve also after this part, after this curve up to this level, so you can think about my approximately it is V is equal to mu E, right? Beyond this curve, what we have observed that it is kind of saturating. This curve is saturating, right? This curve is saturating, and the moment it is saturating, what you have observed, like this is no longer valid. So V not is equal to mu E. This is no longer valid, right? So it happens so like you must be having one velocity which follows a linear relationship. We can write V L, L for linear, and another velocity which is kind of saturation, so Vs, right? And in between that, we can draw a curve which is nothing but up to this point we can write it's a critical velocity. So what I'm trying to tell you, up to the critical velocity, up to the critical velocity, you are following the linear relationship, that is V is equal to mu E. So it is below the critical velocity, and V naught is equal to mu E when it is above the linear relationship. So this is this what we actually assume. Now, if you see the other part, like gallium arsenide, it happens so like you travel a lot than your silicon. So for an example, like if you take here, you see that you have traveled a lot. Okay. You have traveled a lot, and then due to some reason, it has come back to the same. And why it is come back? So we just understood last class. Why? Because it's called that velocity or electron rolling off effect. What is an electron rolling off effect? Like in this critical velocity, which is 3 kilovolt per centimeter, 3 kilovolt. You can see this is my 3 kilovolt per centimeter. At this voltage or at this electric field, what happened? The electron is actually traveling from high mobility region to low mobility region. Okay. And that is why the moment it goes to low mobility region, your velocity actually going down. And that's what we have actually trying, we actually model it here. So you can see this model, right? So what we are feeling that you have an electric field over here. Okay. This electric field actually travel up to this point and then it's rolling off. You have electric field up to this level, then it travel and then it is rolling off. It's very important. And so the reason is that when this electric field, when this electron is in this zone, it is having effective mass, it is low, but when it goes to here, it is effective mass is very high, right? The moment effective mass is very high means your mobility is very low, because mobility is now q tau by m square, right? So that is why we are saying. And this is the one of the reason. And mobility is low means you can see v is equal to mu e. So mobility low means velocity low. So velocity low means it actually come back to your low velocity region. That's what we are saying, this part. Okay. So this is actually low velocity region. So this is my high velocity region and this is my low velocity region. So low velocity and this is high velocity region. So this actually we have started yesterday, last class. No. Okay. Another thing is the same like indium phosphate also. You can see indium phosphate travels little bit more. So it is actually 2.2 and indium phosphate here is actually 2.5. So it travels more. That means for a long range, of electric field, what you can see, my that it follows a linear relationship, linear zone. I mean to say, like if you travel a more distance, I mean like if you apply more and more electric field, so the critical velocity. So okay, so let us try to plot a critical velocity over here. So here is suppose you can see critical velocity for indium phosphate is 10.5. So below 10.5 electric field, 10.5 kilovolt per centimeter below electric field, it is kind of linear, and above it is kind of saturation, right? For an example, gallium arsenide, it is actually 3 kilovolt per centimeter. So below 3 kilovolt per centimeter, it is actually kind of linear, and higher than that, it is kind of saturation, right? And silicon, let's not count over the silicon, because silicon is all over actually rolling down, right? So I mean to say, like even at high electric field, there is a no great improvement of your velocity. For an example, silicon maximum velocity is 1 into 10 to the power 7 centimeter per second maximum, right? Even it is lower than that, 0.8 you can tell. So for an example, like I'm telling about this one, silicon is 0.8 into 10 to the 7 centimeters is definitely low, right? So there is no, like, even there is a, like, you can go up to 10.5. I mean, like what I'm trying to say, like for silicon, you can assume that below 10 point, the critical velocity is very, very low. So below 10.5, you can have something. Above 10.5, you have a saturation. But still, your velocity is very, very small. And if, as long as velocity is small, your current is small. The current small means your GM is small. So there's no point of discussion. Silicon, another thing is silicon mobility is also low. So let's not have a discussion on it. Okay. So we'll have a target compound semiconductor, gallium arsenide, indium phosphate. But definitely, comparison gallium arsenide and indium phosphate, we are preferring gallium arsenide. Why? Because gallium arsenide mobility is high. as compared to the indium phosphate. So that is why we are actually always look the gallium arsenide. Though the saturation velocity or saturation electric field of indium phosphate is little bit high, it's a 10.5 as compared to the gallium arsenide things actually 3 into 10 to the power 3 kilovolt per centimeter, right? So this is that you actually please remember. But it's not that people are not fabricating indium phosphate based MESFET device or HMT device. People are fabricating, but if you want to get a full benefits of out of that MESFET or HMT, gallium arsenide is a natural choice, right? Now, thing is that how it beneficial, what is called the velocity overshoot effect. So let's try to understand this velocity overshoot effect in this manner. As I told you, like, so while we are discussing velocity overshoot effect, just remember our basic structure. And what is our basic structure? So you see that we have a like basic MESFET structure. So source, drain, and gate, right? Very, very fundamental basic structure, right? And what is we have, right? So we are using semi-insulating gallium arsenide. Why are you using semi-insulating gallium arsenide? I said I'll discuss later on, not now, because to create some confusion. Okay, and here you are using entire gallium arsenide, right? Question is like what we are saying, that if you try to reduce the source and drain or L or L, the length between source and drains or whatever, so that means you can tell that if you try to reduce, this is source and drain, right? If you try to reduce L, what will happen? Like the VDS, whatever voltage you are applying. So what is your electric field? Electric field is actually whatever drain to source voltage apply and L. Now if you are decreasing L, so electric field is increasing, right? Now what will happen, that if it increase such a thing, so you will see that for gallium arsenide, if you compare, so you will be always in this zone, means like you will be always in this zone, because suppose 10.5, you see this is actually descending zone, 20 kilovolt, 30 kilovolt, 40 kilovolt, 60, 70 kilovolt per centimeter, all this kind of, you are saying it's actually saturation zone. That means there is no point like of tailoring. Like what I'm trying to tell you, that always the moment you have a velocity and which is actually saturating, it means you have a velocity which is saturating, it means your current is always kind of constant. The current constant means GM constant, right? So you don't have a flexibility, right? So what I need a minimum shrinkage structure, decrease structure, scale down structure, okay, and with a benefit of having higher frequency. I mean to say, like here, suppose if you want to scale down, somehow if you try to scale down, what will happen? Your velocity saturates. And if it velocity saturates, whether it's 1 micrometer, whether it's a 0.5 micrometer, whether it's a 0.1 micrometer or 100 nanometer, doesn't matter. All case, you will get same GM, right? So you will not get, so what I want the moment I shrink it, the moment I reduce the size, I should get some better GM, right? Suppose I want to operate 800 gigahertz, right? So it's a huge frequency. So I have to shrink down. I have to reduce the structure such that I should get 800 gigahertz cutoff frequency or operating frequency. So now, but the problem is that if you reduce it, you will get you'll get a problem in the sense of like you are always in the saturation region, so you will not get a benefit at higher frequencies. After suppose after 300 gigahertz, after 300 gigahertz, whatever you try, you won't go more than that, right? So I mean to say, suppose your saturation frequency 300 gigahertz, and even if you try to reduce it, you are always getting 300 gigahertz, where your target is 800 gigahertz, right? So how to get it, right? So that's the important. So so the thing is that this is possible the moment you have called the velocity overshoot effect. And what is the velocity overshoot effect? The velocity overshoot effect is the following. I should mention the source of this curve, which I have not mentioned, but definitely in okay. So the paper and everything I'll mention in my next class. Since it's an online class, I should give the reference, which I have not given. Sorry for this mistake. Okay. So what is that? What is the velocity overshoot effect? The idea is the very similar. So you see, you have a source, you have a drain, okay, and you are applying drain to source voltage, right? At the moment, let's not draw the gate, just for understanding purpose. So what happened? What happened? You're drain to now, and this L is also is L length. Now the idea is like that. This VDS by L is the electric field, right? This electric field should be high. I mean to say, the moment one electron is coming out, the moment one electron is coming out from the source, immediately what I'm trying to tell you, the following things. Like suppose you have a one electron which is coming out from the source. Okay. The moment it come out from the source, immediately they fell huge velocity. Why? How? It is possible. Just you think about a situation like you have, let me draw the same satellite valley and all these things. Like you have thing is that you if you can remember nicely this electric field, okay, and it is rolling over to the nearest satellite field, and such 4 satellite valleys sit there. Now suddenly it happens so this is one process, and that due to this process you are getting a lower electric field, right? Now that is what we are saying. This is the process for which we are getting a lower electric field. So it is actually velocity, this is electric field, and this is the one process you are getting a lower electric field for gallium arsenide. Now it happens so, suppose suddenly the electric field, this electron in this part, in this zone, suddenly feel a high electric field. High electric field means high energy, right? Because electric field means high energy. So what is the relation? You know that part. Huh? It is a derivative of energy, right? So we have done several times. So the moment you have a high electric field, then what will happen? Instead of rolling over this part, it will jump like that, and then it will come back. I think you understood, like the situation is not a normal situation. What I am trying to tell you, you have a particular electric, earlier you have an electron which is actually rolling down. The moment you have a situation where you apply electric field, it rolling down. Huh? Now, it is looking like a carom board, or like a striker, or something like you are tossing, right? You have something and suddenly a huge electric field the electron experience, right? So it is like electron go fast sometime. Instead of rolling over like that, since you suddenly it feels a huge electron, it goes sometime and then it will come back. It means different. It means like if it happens so the travel, like the velocity is not like, it's not like that, because it travels a lot more distance before it saturates. A lot, so it travel a lot distance, a long distance before it comes and rolling over, right? So that is what. So look at this. This is the curve has been generated, and this is the situation is very simple. Like suppose look at here. What I'm trying to tell you, just look this part carefully. Here you see, you instead of rolling down, so instead of slowly you are giving a voltage, okay, 3 kilovolt or 10 kilovolt. So think about gallium arsenide. Instead of giving 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6, rather than you suddenly give it 10.5 volt. Sorry, suddenly you have not volt, suddenly give 10.5 kilovolt per centimeter, that electric field. So what will happen? You are expecting, as per our things, you are expecting velocity would be like that, but it is not like that. Why? Because as per the overshoot effect, it travels a long distance, then it will come back, right? So how it looks? So this is a plot. It's a drift velocity versus time. Okay, with different electric field. You see 10 kilovolt per centimeter cube, 10 kilovolt per centimeter, 5 kilovolt per centimeter, 1 kilovolt per centimeter, right? This is a different voltage electric field that we have been plotted. What it means? It means suddenly if you give 10 kilovolt per centimeter, huh, so for a particular, and then it travels a long distance, right? It travels a long distance, and that's quite so what I'm trying to tell you. So suddenly if you get 10.5 kilovolt per centimeter to travel a long distance, that means it 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 travels a long distance with some time, right? In your first zone, I mean to say, like here it travel a long distance over here, right? And definitely it and it is actually your move higher zone, mobility higher zone. So definitely, and since it travels, it stays here, it stays, the electron stays here for some time. So definitely it is also have some time, right? Sort of also has some. So that means what I'm trying to tell you, trying to convince you, like the moment you give an electric field at the fast valley where mobility is low, where mobility is high, effective mass is low, in this zone, it stays for long because it jumps, okay, before it comes down to your other value, right? So we can plot the velocity and time, right? So that's what we are plotting over here. You see here, it is nothing but velocity, and here you see it is nothing but time. So this is the thing that we are actually plotting, and you see different voltage, electric field, 10 kilovolt per centimeter, 5 kilovolt per centimeter, 1 kilovolt per centimeter. Look at the change. For an example, like if it is a gradual process, I mean, don't think about like, okay, one thing you have to remember, if you give a slow increase of voltage, like 1 kilovolt, 2 kilovolt, 3 kilovolt, 3 kilovolt per centimeter, 4 kilovolt per centimeter, 5 kilovolt per centimeter, it won't have that much, it won't have that effect. Remember, if you give a slow variation voltage, it won't have a voltage. It is a sudden voltage. The moment electron released from the source, immediately it feels a huge voltage, and that then only the velocity overshoot effect will happen. Okay. So this is what it is actually I'm looking like. So here in this curve, you see it is a slow variation voltage plot where we are expecting my velocity. So my velocity I'm expecting over here, right? In between 1 or 2, suppose 0.5 or 0.6. Okay. So here you can see 0.6, approximately like 1.6. 1.6, 1.8, right? 1.6 into 10 to the power 7 centimeter per second at 10.5 kilovolt per centimeter. But this is actually slow or rolling down effect. This is slow or rolling down effect, right? But the same thing, if you give a suddenly high voltage, what will happen? 10.5, you can see 10 kilovolt per centimeter, same volt, 10.5 or 10 point, doesn't matter, 10 kilo. You will see your approximately 4.8, right? So like if it is a slow effect, you can see the velocity is 1.6 into 10 to the power 7 centimeter per second, where here you are saying velocity not only it's not 1.6, it is 4.8, around 3 times higher, right? So it is like 4.8, 10 kilovolt per centimeter. Okay. So if it is instead of 10 kilovolt, if you give, I assume 10.5 kilovolt, so you would have reached 5 into 10 to the power 7 centimeter per second, right? So that means you have a higher velocity. Higher velocity means what? Higher velocity means higher current. Higher current means what? Higher current means better GM, better transconductivity. Now, see, look at this part. So you have a 10 kilovolt per centimeter, 5 kilovolt. So each and every voltage, each and every electric field, 5 kilovolt per centimeter, it looks like that. So suppose suddenly instead of 10.5, instead of 10 kilovolt per centimeter, suddenly you give 5 kilovolt per centimeter, what will happen? It will actually travel approximately 3 into 10 to the power 7 centimeter per second, that velocity. But still it is higher. Similarly, 1 kilovolt per centimeter, we are not seeing any benefit, right? Because it is like a 1. So it is almost 1, right? So that means now you have a time over here, you have a velocity over here, and you have a different variation of electric field. So definitely you can plot it. You can actually suppose you have a time and you have a time, and so you can easily and you have a velocity, so you can easily plot, right? You can easily plot the distance, right? Because if you know the velocity and if you know the time, so you can plot the distance, right? So that is what we are plotting here. They have, the scientists have plot. So instead of this axis, they plot distance, okay, versus drift velocity. Why they are actually saying like that? This portion, if please try to understand. Suppose one person came, one user came and asked you, okay, I want to fabricate, I want to make a mixer, okay, or a convolutor for communication system at 800 gigahertz. Right? So that is actually he or she said about your requirement. 800 gigahertz is my thing. Now, can you fabricate a low? Can you fabricate a very small version of MESFET? Can you fabricate a small version of MESFET? Very, very small. See, you can easily fabricate a long channel MESFET and you can achieve something, some level. But problem is that if you try to fabricate a very like 800 gigahertz with a small thing, so then it would be really problematic, right? So, uh, So what you have to do, you have to immediately try to understand that, okay, 800 gigahertz first. So whether it's a short channel or long channel, okay. So which policy you have to take? So definitely you have to take a short channel because the customer needs very small distance, small dimension. Okay. So what is the dimension? The first thing that you have to figure out, what is the distance between source and drain, so that we can have a 800 gigahertz. Now, since you know, suppose I know FT is equal to 800 gigahertz, right? And what is the frequency? FT is GM by something, right? You know that part? GM by something, right? Now, the C capacitor arrangement, this capacitor arrangement that depends on the fabrication, which type of geometry you are taking. For our case, this capacitor arrangement is very peculiar. We have to very consider that depends on what type of Schottky junction you are taking, right? So whether it is a gold gallium arsenide or like platinum gallium arsenide and all these things, right? Not only that, we have to really think about how many defects are there. So all these things we have to read. So it's a particular arrangement. If you have that particular arrangement, if something your reference thing, then you have to think about what is my GM. Okay. So for this 800 gigahertz, what I have to achieve GM. So that GM you actually fix. Once you fixed your GM, then you have to fix what is the current range I have to get, IT total. And if you want to get a current, so what is the current that you are actually about, you know, your current is IT, you know, that is same is mu CS W12. Okay, all these things, right? If it is my saturation, so all these things. So all these things that you can calculate. So you need to have a IT is mu, that is 8,500 centimeters per second at the moment. Capacity CS, that actually your choice. Why your choice? So whether you have to take gold gallium arsenide or platinum gallium arsenide or this one, so that is your choice. And not only that, what is the doping level that you want to have? Because the CS, you know, the CS is equal to epsilon by D, right? Right. So this XD, D means actually depletion layer. So this depletion layer is also function of your gallium arsenide doping. So all these things. Similarly, W by L. So this W by L, as you know, that we cannot play too much. Why? Because the customer is always asking what he is asking. He is asking, I need to have a very miniaturized version. So we cannot go more than that. So W by L, you have to be as small as possible. And here is the designer beauty. Suppose you are the designer, so definitely you have to take confidence that W by L ratio should be such that which is good enough for fabrication. So for an example, how it depends on, suppose student one, he is having one fabrication laboratory where people have optimized a particular dimension. Like this, they are saying like, okay, below 0.5 nanometer, I cannot go because my laboratory, the instrument is such that I cannot go below 0.5 nanometer. In this case, and but now the user is coming to you, right, to have a miniature version. So you are limited to 500 nanometers. So then you have to, but still you need to go 800 gigahertz. So you have to do something. You have to change other parameter, like how to increase CS capacitor. So if you want to increase CS, you need to increase your XD has to, sorry, if you want to increase this one, so you need to reduce it. The XD you have to reduce it, and if you want to increase if you want to reduce the XD, what will happen? NA has to increase. But problem is that the moment you want to increase the NA, your mobility will decrease. So you see the problem, it's all actually related. It's not so straightforward, right? So you have to be very careful. And and take the challenge, right? So that's what I'm saying. Anyhow, what I'm trying to tell you, so if any user is coming and telling that I want to fabricate a 800 gigahertz cutoff frequency transistor or a modulator, so you have to be very careful about it, okay? So you know, for 800 gigahertz, what would be my GM for a particular dimension of CI? CI means input capacitance. How the input capacitance and that part, so that definitely you know from your graduate degree course, like how to calculate CI and all these things from any transistor, you know that part, right? So that's not a important part, right? So I'm not telling about. So all these things. So now what you have to take for a particular CI combination, you need to find out GM, and once you know the GM, and then you have to find out particular IT corresponding to this GM, and that you have to be very carefully adjust this parameter, right? So that you are in confidence zone to fabricate this device, right? Now to have such kind of things, the first thing you have to fix, because 800 gigahertz has been fixed. So L, what would be my L? Length between source. So what would be my length? Right? So that you can calculate, and that is kind of fixed. For an example, you know, as I told you that, so we have to calculate L, or we have to calculate this L for distance, right? So now you see, then you have to, so each and now, okay, now velocity and GM is related, right? Because you know that your velocity is related to current, so current is related to GM, so it is all actually related, right? So no issue. So for a 800 gigahertz, for 800 gigahertz, you need to find out which, what would be my distance, what would be my distance, what would be my L. Suppose for 800 gigahertz, suppose for 800 gigahertz, I need to have a L of 4.5. Okay, so that is actually, you understand, no? Like when you put, what is that? That you can understand, because you know when you open this expression, you know what would be my best combination, what would be my best combination, so that I can have my GM or velocity, right? So what would be best combination, what would be my best combination, for which I need to have a particular velocity, because IT is related to, right, Q and V, right? So you know what is the velocity for which I can get this current, right? So that means, so we have to have a, we have to find out particular velocity out of that. Okay. So what is the velocity? Suppose 4.5, 4.5 V you need, right? Now you see, if you want to have a 4.5 V, what would be my distance, length? So 4.5, so this is my 4.5. So approximately it's actually maybe 150 nanometer, right? 0.1, so it is maybe 0.15, roughly, huh? Micrometer or 150 nanometer. So that means you have to choose, if you want to shoot out at 800 gigahertz, you have to choose 0.15 micrometer, right? So your L should be 0.15 micrometer. Based on the L distance, so you can actually choose your W, right? So W by L distance, so you already get L, so you have to choose particular W, so that you will get a particular combination, right? So that you can get 800 gigahertz. Suppose somebody is telling, okay, I want to have, I want, for my design, I want to have a drift velocity of 2 gigahertz. Sorry, I want to have it for a particular frequency. Somebody else, for a particular frequency, found out that I want to have a, I want to have a 2 gigahertz. Sorry, 2 into 10 to the power 7 centimeter per second, right? That actually I need, right? So what is that? So you can have a luxury to go 400 nanometers. So this is actually suppose 400 nanometers. So your length can have a 400 nanometer. Now the question is like, suppose by any mistake, I have taken, suppose you have a source and drain. Okay. So this is source and drain. Okay. And suppose it is 1 kilovolt per centimeter or 0.555 kilo. So L is actually maybe 1 micrometer. Suppose L is equal to 1 micrometer. Just for an example. So what will happen? Okay. Now, thing is that this is because your length is very high. So what will happen? Length is very high. The like now, what will happen over here? So you might get, and this high length, you have a high length, and in this high length, suppose you get 10 kilovolt per centimeter. Means like what? There would be two conditions, right? Don't confuse. So one is actually short channel, where you are giving source and drain of 10 kilovolt per centimeter, and there is actually, suppose this is actually 150 nanometer, and here what I am saying, it is actually what is actually same 10 kilovolt per centimeter, but long length, L is equal to 1 micrometer. So here actually we understood, right? Because we got the curve based on that. So if you got, but here you see the long channel, you'll see the problem is the following. You might get a high electric field, sorry, high distance. So what will happen? You will get high part, right? But so up to here, you can see from here to here, this is high, no? So up to here you see, you'll get you will get a high velocity. Up to this part, you get a high velocity. Okay. But before this electron reached to drain, no, sorry. Up to this length, you are getting high electric field. But this electric field, sorry, and here actually my velocity is like v. So up to this distance, suppose L, right? L small. Okay, you are getting high electric field. High velocity. But what happened? The problem is that electron is not ending here. Electron is still further actually traveling, right? So when it travels and reach over there, you will get the velocity of this one, right? That is why it is telling, this picture is telling, you look at that. You look these things very carefully. What is happening over here? What is 5? So here you are getting 10 kilovolts. So this curve is for 10 kilovolt per centimeter. But you are, suppose you are, and you have source over here, and you have a drain over here. Means you are actually catching the electron. You are receiving the electron across this distance. Now the problem is that you might have achieved 10 kilovolt per centimeter. You might have achieved huge velocity at this point. The problem is that I should be getting the effect while when I capture this electron to the drain, when it reaches the drain. But that's what I'm saying. You might have got a huge field over here, but by the time it reached to the drain side, you have come down to 5 kilovolt per second. You have come down to 2 into 10 to the 7 divided by centimeter per second. So that much velocity, right? So if you have a, so what I'm trying to tell, so suppose you are applying 10 kilovolt per centimeter for small and large distance, or for large length, large distance, you have to catch this electron before it saturates. I mean to say, right here in this case, you see your distance is 150 nanometer. Just now we see, and it looks like that. If you try to voltage and distance, what I'm trying to tell you, so that means you are catching. So you are catching the electron. The moment electron is released, it is gaining huge electric field, and the moment it reaches to drain, it is also like you are catching this electron across the drain with a high velocity, right? So that's what I'm saying. So this is actually all. So your source and drain position should be such that it's across the tip of this velocity curve, right? So I mean to say, like, you should be very careful before you design things. You should be thinking, like, if you want to have a particular GM and corresponding to what is the electric field. So suppose you want to have an electric field of 3, and which is corresponding, suppose 1 micrometer, 100 nanometer, right? Your source to drain distance should be 100 nanometer. If your source and drain distance more than 100 nanometer, what will happen? You will slowly, because this curve is falling down. Remember, this curve is falling down, right? The moment you increase the distance, what will happen? You will be catching this electron across the drain at very low velocity, right? Because the curve, this velocity is falling down with the distance, right? So that actually you have to remember. Okay. So I'm stopping over here, and next day I'll start HMT, but before that I'll post a homework about the modeling of MESFET, because the input is like different type of, like, suppose I am coming with the input. Suppose somebody is giving an input like, I want to design 500 gigahertz. Now you design a MESFET, right? So that would be your things, but I'm not going to give you like this much thing. So I'll give you step by step. So first you calculate GM, then calculate I, calculate velocity. If you follow these steps, ultimately you will get an answer, right? And that homework would be the modeling of MESFET, right? So suppose a user comes and tell you design a 300 gigahertz of MESFET, how to do it. So only thing is that since I'm not giving you that as a straightforward, rather than I'll split this problem step by step, which you should remember before you design MESFET. Suppose sometime I will ask you to, they are actually, we have to, I can ask to find out A means the thickness of this gallium arsenide, mobility, all these things I'll ask. So only thing is that it is a step by step method to remember, to understand how to design a MESFET. Okay, as a user point of view, or as a, like, you take a user input and you have to design your MESFET. Okay, this is a very basic. There is also complicated design is there, which I am not giving, and it's not scope of this course. Okay. And another thing is that I would like to ask you, like, how far you have went about your micro nano fabrication technology? Now, what is you are actually studying now? Have you done photolithography, oxidation, diffusion, RI, ion implantation? Have you done all these things? Because then I had to take up the MESFET fabrication. Hello?
So currently we are studying sputtering and physical vapor deposition, those techniques.
Okay.
Thin film deposition.
Sorry?
Thin film deposition techniques.
No, thin film. I'm just asking, so oxidation, diffusion, ion implantation, and lithography has not been covered yet, right? Have not been covered. So only you are in the thin film deposition, correct? Sputtering or maybe physical vapor deposition, right? That's what you are saying. Hello, speak out.
Yes, sir.
Okay. So once your photolithography and ion implantation is covered, so please let me know, because design is fine. So after this course, after this discussion till now, remember it's so pathetic because whatever we have discussion just now completed today, only you think you can design a MESFET, that's all. But you cannot fabricate a MESFET. So fabrication things is little bit different. Once you know, once you design what is the thickness of A and all these things, then we have to turn out how to fabricate these things. So that I need your help once you know about this part, right? So in this case, what I'll do, next day I'll start HMT. Okay. And once HMT is over, so I'll come back again and I'll discuss about how to fabricate MESFET or HMT. I'll take only one example, either MESFET or HMT, because HMT is a modified version of MESFET, right? So if you can cover MESFET, you can fabricate HMT, or if you cover HMT, you can easily fabricate MESFET. Okay. So thank you. And tomorrow we have a election. Tomorrow we cannot have a lecture.
Hello, sir.
Yes.
Sir, regarding the video lectures, we haven't received any
Sorry?
lectures after this one.
Sorry? Hello?
So, video recordings, regarding the video recordings.
You want the video record? I'll send you. But
Okay, sir.
send you only Thursday after the election. Kerala government election is going on. So after the election, we can send. You have to go for election.
So, election is tomorrow.
Yes.
Okay, sir.
Yeah, tomorrow no class.
Okay, sir.
No, we are actually ahead of time. Don't worry. Since I'm not discussing micro nano fabrication technology, no. So I think it would be repeating. So I have plenty of time. So you can go comfortably. No issues. Okay. Thank you.
Thank you, sir.